So my name is Zach Shwirep-Conti, and I'm a research fellow, I always get this wrong, at the Alan Turing Institute in London. I would also like to introduce my colleague and the co-organizer of this seminar series, Andrea Pizzoferrato, who is a visiting academic at the Turing. For those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. If any of you are interested in sharing your work in any of our upcoming seminars, please feel free to get in touch with either Andrea or myself. We'd be happy to host you. Questions may be asked towards the end of the seminar, unless our speaker for today does not mind questions as we go along. These may be done in person by using the raise hand function or via Zoom chat. And okay, so without further ado, I'll ask my colleague Andrea to invite our speaker for today. Thank you very much.
Thank you, Zach. So Ameya is currently an assistant professor of applied mathematics at Brown University in the US. He holds a PhD and master's degree in aerospace engineering from the Indian Institute of Science, grounded with a bachelor in mathematics from the University of Madras. His research journey includes postdoctoral work at both the Tata Institute of Fundamental Research, Center for Applicable Mathematics in India, and Brown University. His academic journey is further enriched by his experiences as a visiting researcher in Luxembourg and Germany. Ameya research expertise lies at the nexus of mechanical aerospace engineering, applied mathematics, and computation, with a special focus on scientific machine learning algorithms, but integrated data with physics. Today, Ameya is going to talk about enhancing scientific computing through physics-informed neural networks. Without further ado, Ameya, the floor is yours. Thank you again for joining us.
Yeah, thank you, Andreas, for the nice introduction, and I would like to thank both Zach and Andreas for the kind invitation. So today I'll talk about basically PINNs, so physics-informed neural networks. So I'm sure most of you already know about PINNs. So most probably, mostly I'll talk about my work, which I did in this area. So let's start. Let's start with the overview. So basically, I'll first quickly go through PINNs. We will also see some of the performance improvement techniques, and we will also discuss some of the applications where I use PINNs to solve the scientific problems. I'll also discuss two domain decomposition based method, which is conservative PINNs for specifically tailored for the conservation laws, and more general extended PINNs. So general in the sense that you can decompose both in space and time, unlike cPINN. And I'll also discuss the recent extension, a unified scalable framework for time domain decompositions. So, okay, scientific computation. So we all know that traditional approaches like finite element, finite difference, and finite volume method have undergone remarkable progress, but they still operate under very stringent requirements. So basically, they need a precise knowledge of the underlying physical laws, initial boundary conditions, and they often need time-consuming workflows such as mesh generation and the long-time simulation. Okay, on the top of this, if you are actually simulating a ill-posed inverse problem, so it can become a very costly because you have to do all this simulation multiple times, either to discover missing physics or to calibrate the free parameter in the model. So I'm talking about this small region, the red box here, where we have some data available, and at the same time, some physics is also available, and we are trying to find out the missing parameter or some missing physics in the model. So on the top of that, if you have data which is dinky, dirty, dynamic, and deceptive, then it's a problem for the traditional numerical method. So these methods suffers sometimes it is difficult or sometimes impossible to solve such problem using traditional numerical methods. So the idea here is we can actually use the physics-informed machine learning, in particular physics-informed deep learning. So I'll go through a quick survey. Basically, this idea is not new. It was proposed back in late 90s by Lagares. He used neural networks to solve PDEs. Recently, it was used by OADI for the multi-scale dynamical system, and SINDI framework for dictionary learning of the dynamical system by Brunton and others. And then Karpatne, physics guided neural networks, he proposed in 2017. By the way, PINN also came during 2017. So the first archive version of PINN was in 2017, but it was published in JCP in 2019. So basically, in this talk, we will focus on PINNs. So there are several methods like PINNs, physics guided, physics informed, physics constrained, and so on. So what is PINNs? So PINNs basically essentially defines a paradigm for bridging physical model and the observational data. So idea is very simple. So I assume that you are aware of the neural network and the, of course, it's a data science institute. So you have a neural network, feed forward neural networks. My input to the neural network is basically independent variable X and T, and my output is the solution U. So in this case, solution U not just satisfies the data, which is coming either from the experimental measurement or initial boundary condition, but it also satisfies the PD. You can see this box physics informed part. So basically, here we are using automatic differentiation to find out all the derivatives involved in the PD. And your loss term at the down consists of the data mismatch term, that's the first term, and the second term is the PD residual. Okay, so the aim here is to minimize the loss term so that we can actually get the optimal parameters theta tilde, which consist of all the weights and biases. And that's how you actually solve the solution. So what you did, you actually recasted the original PDE problem into an equivalent optimization problem. Okay, so what's the advantages of solving this? You can solve both forward as well as ill post inverse problems. So that's the advantage here. So please feel free to stop me if you have any questions. I don't mind. So okay, let's see. Let's see first a simple pedagogical example. So we have a viscous Burgess equation. It's a 1D equation. You have unsteady term, nonlinear convection term, and the linear diffusion term. My initial condition is just a sine wave, and my boundary conditions are 0. So I'm using around it's 100 data points here, not 150. Residual points are 8,000, randomly chosen in the domain. Activation function is tan h, learning rate, and optimizer. So here I am using optimizer Adam followed by the LBFGS. So that's the solution. You can see these 100 points randomly chosen from the boundary and the initial condition. And here I'm comparing the exact solution with the prediction by the neural network. So here the L2 error is in the is of the order of -3 basically. And here is the Adam and the Adam loss function, which I use it just for 100 iteration, and then I switch to LBFGS till 5,000 iterations. So idea is very simple. As I said, you just need to minimize the loss function, and then you can actually, it's basically a regression problem. So we are not doing any time marching schemes here, like the traditional numerical method. Okay, so I'll next describe my work on adaptive activation functions. So basically, this is one of the important hyperparameter of the network, and that actually introduces nonlinearity. So it is not known that how to choose this activation function. So basically, there are many open issues while training, like vanishing and exploding gradient and the plateau phenomena. Uh, However, the empirical observation, we actually know that a well-chosen activation function can help the gradient descent to not only converge fast, but to generalize well. Okay. And some of the desired features of activation functions are nonlinearity, continuously differentiable, and the range. However, there is no rule of thumb of choosing optimal activation function. So that's basically the motivation for the adaptive activation function. So you start with one activation function, and as per the problem at hand, you can adapt it. So how to do that? So, well, here your phi is the activation function, and it's the input to the Z is the input to the network, and this is the affine transformation given by this calligraphic N. So basically what I'm doing, I'm introducing just one constant here, N is fixed, which is a positive scaling factor, and A is the tunable activation slope. Okay. And I'm initializing that as always equal to 1. So N is equal to always 1. So why 1? Then you actually start with your original activation function, but then you are giving an additional activation slope as a parameter, which can be tuned along with the weights and biases. And you can see here that for different values of A, your activation slope is changing for different activation functions like sigmoid, tan H ReLU, and the leaky ReLU. Well, this is a global parameter. That means you just define one parameter for the whole network. But this idea has already been implemented by NVIDIA in its software, Modulus software, which was previously called as SimNet. You can actually do the same idea locally. That means instead of introducing a single global variable, you can actually introduce a layer-wise A for K layers, or even neuron-wise A. So that also improves performance because of additional degrees of freedom. And in terms of computational cost, you can see that compared to the number of parameters, weights and biases, these number of A are very, very less. Well, this theorem, we proved it in the original paper. You can see the reference here. So basically, this theorem says that this we proved that for the gradient descent method, which is the most basic form of the optimizer. It says that if you have one of the three condition holds, constant learning rate, diminishing learning rate, and the adaptive learning rate, then we can actually avoid the suboptimal critical points or local minima. So you can the proof is very simple. You can see this reference for the proof. So I'm not going through the proof here, but if you have any doubt, you can email me later. Yeah, so this is one more idea we propose. It is called Kronecker, deep Kronecker neural network. So idea is simple. So instead of a single activation function, phi or phi1, we are actually adding the series of activation functions, phi1 to phi k. Okay. And the particular case is the rowdy activation function. Rowdy means oscillatory, noisy. So you can go with phi1 as any standard activation function like tan H or ReLU or anything. And the remaining phi k from small k equal to 2 to capital K, we use these sinusoidal functions. So basically what we are doing, we are adding a noise on the top of my base activation function, the standard activation function. And again, these here not only slope, in this case, the frequency of sinusoidal wave is tunable, but also amplitude is also tunable here. Okay. So what's the advantage? It can actually overcome the spectral bias problem. So if you are actually trying to simulate a very, a solution containing very high frequencies, then this the rowdy activation function helps, because you are actually tuning these high frequencies waves, or the activation functions also here. So you can see one example. So let's start with a simple function. It's very smooth. For the from to 3, that's the domain, and adaptive activation function tan H, and the loss function consists of just a data mismatch term. So here is the results. So you can see on the left hand side we have fixed activation tan H, and on the right hand side we have adaptive activation function. So you can see that the black line gives the exact solution. So even after 22,000 iteration, the yellow curve with cross, it couldn't capture the solution. But with adaptive activation function, you can see that it nicely captures the solution. So let's see the loss function here. At the bottom, you can see the loss function. The red one is for fixed activation function. It's stuck in the local minima. It's not going down. And if you see the green color curve dash line, you can see that it is actually going much faster. And on the right hand side, you can see that this variable NA. So here N was 10. So A I initialize as 0.1 because we had to initialize NA is equal to 1 unity. So we start with 1, and you can see that as NA adapts, your loss function is going down accordingly. And then after some time, actually NA value saturates. So there I stopped. Okay. So you can see that just single parameter can actually increases the convergence really fast. Let's see one more example. So it's basically PINNs. It's not a function approximation. And here we are solving the 2D Helmholtz equation. We assume the solution is in this form, sine pi x, 5 pi x multiplied by sine 10 pi y. So it's not that high frequency, but still it contains small frequency. So again, activation function is tan h. Both adaptive and fixed I used. Residual points 8,000, data points 200, and the optimizer is Adam. So you can see that the blue curve, this is the loss term, left-hand side, and the right-hand side is the related to L2 error. So blue curve is the fixed activation function, tan h. The green one is a locally adaptive activation function. That means at each layer-wise locally. So at each layer, we are introducing the parameter A. And you can see the red one is the rowdy activation function with 5 terms. So K is equal to 5. So you can see that the relative L2 error in case of rowdy is decreasing much faster compared to fixed. And of course, compared to the layer-wise locally adaptive activation function. Okay, we have also written this survey recently. Here, basically, we compare different activation function for both regression and classification problems and their performance using different machine learning libraries. So,
Ameya, before you continue, there is a question from the audience.
yes.
So from Anmar, so the first question is, why in example 1, you switch from Adam to BFGS optimizer?
The pedagogical example. Okay, this, okay, yeah. This one, right?
Yeah.
Yeah,
I think so, yeah.
Basically, Adam is the first order optimizer and LBFGS is the second order optimizer. So basically, if you directly start with second order, it may stuck in the spurious local minima. So this is a general rule that you start with a robust first order optimizer, and after some time you switch to the second order optimizer. So that's the way to go for optimizing.
And the second question says, regarding the activation function, did you have a chance to check Swish activation function?
We compare different, as I said here, we compare different activation function, more than around 180 activation function in this paper. And we do use we do compare Swish activation function. And we, of course, there is you have a parameter there also in Switch. So we have given all the results. So I would suggest you to refer this paper for proper comparison.
Okay, thank you.
Okay.
Sorry, we have a question from Tariq. Tariq, you can go ahead and ask in person.
Okay. Yeah. Sorry. Okay. I hope you can hear me.
Yes, I can.
Okay. So what I saw about these rowdy functions, this adaptive functions, they're already in sign format, right? And also solution is already in sign form. So do you think it's just like coincidence, or because I don't know, it would be really nice to have at least solution as maybe function of something completely else than because I know that if you are using some similar, or at least if your solution is sign based and if you are using sign activation functions, it really helps a lot. But we don't know the solution most of the time. It's really random. So
yeah, that's a really good question. But here, yeah, coincidentally, both are sinusoidal. But in the original paper of Rowdy activation function, we have solved several examples where solution is not in the form of sinusoidal function. But the point here is when you add the sinusoidal noise, it can adjust itself according to the frequencies. So you can actually tune these frequencies. So that's the whole point here. So if you have a randomly, varying function with kinks and discontinuities, that has also I have shown in the original paper that the Rowdy activation function captures those kind of solution, irrespective of the behavior. I mean, if it is not even sinusoidal, it's still fine. So this is just an example I gave, but coincidentally, it was having the same kind of solution. Okay, so let's move on to the some of the applications. So this is the first application we solved back in 2020s for high-speed flow, basically. I'll just give an example here. Here, this is an semi-inverse problem, and the aim is to solve this problem using Schlieren data. So we have the density gradient, and we also have some pressure data, which is both are coming from the experiments, and the inlet condition. So basically, I'm solving this oblique shock wave problem. So this is XY plane, and you have an oblique shock, you can see here. So that's the steady state solution. So the idea here is if you know the field variable, I mean, given by Schlieren and the pressure data and some inlet condition, not everywhere in the domain, but at specific locations, then can we infer the equation of state? That means the gas constant gamma. So we use air here. So gas constant gamma value was 1.4. That's the true value. And then we use randomly two set of points. One is randomly chosen points on the left-hand side, and one is the clustered point along the shock wave. So, well, how do we know where to cluster? Because we have Schlieren data, right? So Schlieren data can actually give you density gradient, and that's the input you are giving. So you know where to cluster the points. So you can see that the random, okay, and we also use clean data, 1% noise and 2% noise. So you can see that for the, in all cases, the random values are not that good, close to 1.4, but compared to cluster point is very close to 1.4. And this is obvious because cluster point gives you much better information about the orientation of the shock, and slight change in the orientation of the shock can give you completely different gamma values. So this was the one of the inverse problem we solved here. Next, we also use PINNs for quantifying the material properties, and specifically the polycrystalline nickel material we used here. So here aim is to find out the spatial variation of the compliance coefficient matrix using only displacement data. So we received the experimental data from Army Research Lab, ARL, about the X2 displacement, and we used FEM software basically for finding out X1 and X3 displacement. So with that displacement, the job was to find out the compliance coefficient. And so this is a polycrystalline material. So we need to find out what kind of material it is and if it is a single crystal or a polycrystal. So first we just compare the displacement data obtained from the PINN with the actual data. You can see that at 4 locations, you can see the comparison of PINN data with the actual data, and it matches really well. Okay, so these are basically a time snapshot. Okay, for a single crystal nickel, the speed of second shear wave mode is 2.97 millimeter per microsecond. And when we plotted the speed of second shear wave, so we can see that on left-hand side plot, you can see that it varies from 2.95 to 3. Okay, so that confirms two things. First, it is a nickel material, definitely. And second, it is not a single crystal, because you can see the spatial variation of the second shear wave. That means it confirms the polycrystalline nickel material. Unfortunately, the data, the displacement data was not enough to capture the polycrystalline boundaries, the crystal boundaries basically. But we at least confirm that this is a polycrystalline nickel material. And on the right-hand side, you can see the spatial variation of C44, which is the compliance coefficient here. So let's move on to the one more inverse problem. So it's an inverse water wave problem. So I'll explain the problem here. So here we have we need to infer, the aim is to infer the transient velocity field u bar and the corresponding forces on the walls using only water column height. So we have eta, which is actually a water column height, and this height is actually, it is coming from the experimental data. So we have gauges that actually gives a time series data for eta. So you can see here. So this is the xt plane, and we are placing gauges from -40 to +25. So you can see these black dots here. So these are the gauges which are placed along the x-axis, and it gives a time series data. So these are the data, black dots, which is available. Okay. So that's the only data available for water column height. And our aim is to not just predict the water column height in the rest of the domain, but also the velocity u. And if there are walls, then the pressure also. Okay. So you can see that here we use 12 gauges, and here we use 20 gauges, and we reconstruct the both water column height as well as the u predicted velocity. And you can see on the right hand side the pointwise error. So the maximum pointwise error is 0.05 -2 in both water column height as well as in the velocity. Okay, so and as you increases the number of gauges, you can see the error actually decreases much faster in both eta and the velocity field. We solve one more example basically. So here you can see a bar. It's basically a wall, and the wave is coming here, hitting the wall, and then it is going forward. So basically, since it's a symmetric problem, we just use the upper half portion for the simulation. And you can see here, this is the wall. You can see three sides of the wall. So left-hand side is wall 1, top is wall 2, and the right-hand side is wall 3. And we use two set of data. One is low fidelity data given by black dots, and one is high fidelity data. So high fidelity data is around 50, and low fidelity data is around 1000. Okay, so here we use multi-fidelity neural network, basically PINNs. So idea is to map the low fidelity solution into high fidelity one. And once we mapped it, once we learn the correlation between low and high fidelity data, then feed that high fidelity data into the PINN network. So here I have just shown this reference versus predicted low and high fidelity data, where we mapped using a multi-fidelity neural network, and then we feed it to the PINN. So, and you can see the force here, the top row on wall 1, wall 2, and wall 3. And the reference is given by black, and the PINN solution from multi-fidelity data is given by the red dash line, and it is matching really well. On the bottom row, you can see the pointwise error, which is of the order of -3, -4. So here we not only, so the idea here is to, from water column height, infer the velocity, and from the velocity infer the force here. Okay, so let's see some of the limitations of PINN. So PINN is still a developing method. So there are some limitations, and two main limitations are, first one is due to high dimensional non-convex optimization problem, the accuracy of the method suffers. So we usually get accuracy in the form of -5, -6, but it all depends on the optimization algorithm also. So second limitation is the large training time compared to the traditional numerical method. So here we are actually tackling the second problem, large training time. So there are several approaches to tackle this problem, classical approaches. The first one is data parallel approach. So idea is very simple. You have a big data, which you cannot fit into a one GPU. You split that data into number of processors, which you have. In this case, it's 4. And you use the different GPU for each data and use the same neural network here. And since this neural network is, working with different set of data, you will end up with different loss function. Okay. And once you get this loss function, you actually use the all reduce operation to average it out, average the gradient of the loss values. And then you send these average values to the communicator world through the broadcast operation, and then you update the weights and biases or the parameters of the network, and then this way you can actually deal with the high or large data set. Second approach is model parallel approach. So here you split the data into batches B1, B2, B3, B4, and you assign each layer of the model to the number of GPUs. So if you have 4 layer, 4 GPUs. And then layer 1 will actually start working on B1. And once it finishes that working, it will actually pass B1 to L2 and it will start working on B2. So this is the pipeline approach of working. So you finishes both forward and the backward pass with this approach. And then at the end, you update the weights and biases for each batch. Okay. So this is another approach. But if you see in both data parallel approach and the model parallel approach, we are using single neural network. So neural network is same here. So our approach was domain decomposition based PINNs. So idea is very simple. You have a domain, you split it into number of subdomains, and instead of single PINN, you actually deploy multiple PINN in each subdomain. And now, along with the data mismatch term and the PD physics informed term, you also have the interface conditions to stitch the subdomain. And that actually gives you additional term interface loss condition. Okay. So let's see what are these. Okay, before that, let's see the advantages. So it has a parallelization capacity, right? Just like model parallel and the data parallel. But then we have seen the additional advantages given in blue, like local representation capacity, because we have different neural networks in different subdomains. So we have local representation capacity, and we can efficiently adjust all the hyperparameters in the network. Okay, so that's another thing using meta learning. And we also observe reduction in error propagation in the domain. So because we are enforcing additional interface condition here, so that actually act as a regularizer, and it reduces the error propagation in the domain. So first idea is conservative pins or cPINNs for the conservation law. So interface conditions are very simple though. So the first interface condition is the flux continuity condition. So that's the basically we use it for finite volume methods. So here we are enforcing the flux continuity in the normal direction. Okay. And that's why you have dot n here. And the second continuity condition is the average continuity condition. That means we are enforcing the solution equal to the average solution given by this double arrows, double curly brackets, sorry. Why we need this, the average solution? It's very simple. If you have a smooth solution, then average value boils down to the solution continuity condition. But if you have the discontinuous solution, which you may have in case of hyperbolic conservation law, then you are actually enforcing the middle point here at the shock. So it's like 1-point shock capturing scheme kind of thing. Okay, so that's the idea here. So let's take the same example which we have seen earlier. So it's again a Burgers viscous Burgers equation, and we are splitting the domain into 4 subdomains. You can see these 3 lines, white lines. Subdomain 1 is the bottom one, and subdomain 2, 3, and 4. You can see all the hyperparameter assigned in these subdomains. And I have plotted the pointwise error on the right. Well, the bottom figure is interesting. So you have relative L2 error without average term and with average term. Okay, so without average term means you just use flux continuity term but no average term, and then use both flux continuity and average term. So you can see that with average term, the relative L2 error is going much faster. It's reducing much faster than the without average term in just 15,000 iteration. Okay. We have solved this lead-driven cavity problem in compressible Navier-Stokes. So we just divide the domain into 12 subdomain, and these are the hyperparameters: number of layer, number of neurons, and the number of residual points in each subdomain. And we just this is the Reynolds number 100, Reynolds number, and we just compare the PIN solution, cPIN solution with the GIA, so which is matching really well here. Okay, let's move on to the inverse problem. So basically, we have a library term ut plus ux, that's unsteady term. Unsteady term, non-linear term, convection, linear convection with beta coefficient, viscous term with nu, and dispersion term with alpha. And our aim is to identify alpha, beta, and nu with a given data from viscous Burgess equation. So if we know that viscous Burgess equation is there, then beta should be 0, alpha should be 0, and nu should have some positive value. So that's our viscous Burgess equation. So again, I use the same 4 subdomains, and I initialize this alpha, beta, and nu differently in 4 subdomains. You can see these 4 different curves, and the exact solution, exact value is given by this dash black line. So you can see that they actually coalesce all the 4 different curves, and then they move towards the exact solution. Exact solution beta and alpha, they are both 0. But if you see nu, it's interesting. So it is actually, or I mean, it is crossing the exact solution. Okay, it is going away from the exact solution. Why? Because till now alpha and beta, that they didn't converge to the exact solution, and as soon as they become 0, nu started going towards its actual value. So you can see this comparison here. So exact values of alpha, beta, and nu, and the predicted values of this nu, this parameter using sweeping. So they are pretty much accurate here. So what next? We can actually use domain decomposition strategy for every PDE and not necessarily for conservation law. And maybe even in time, we can use this strategy. So yes, we can do it. The answer is XPINN here. So here, idea is simple. Again, we use the average solution continuity condition. And instead of flux continuity, now we have a residual continuity condition. That means we are saying that along the interface, my residue should be equal. Okay. If you have additional continuity conditions, then you can add like derivative, higher order derivative, continuity, or integral constraint. What are the advantages over cPINN? You can extend it to any differential equation. You can do generalized space-time domain decomposition and not just space decomposition. And a simple interface condition. That means we don't have to find out the normal direction in case of flux continuity condition. So that's about the implementation wise. So here is a quick comparison between PIN, cPINN, and XPINN. So we have a special domain decomposition capacity in cPINN and XPINN, parallelization capacity, localized representation, efficient hyperparameter adjustment, and applicability. PIN can be applicable to any differential equation, cPINN for conservation laws, and XPINN again for any differential equation. Interface condition is complex in cPINN in terms of implementation. Specifically, when the interface is moving, then every time you have to calculate the n values. It's simple in XPINN, and of course, XPINN has additional advantages of time domain decomposition. Let's see the same example, Burgess equation, but now our domain is this dolphin shape and the blue sea water outside. So that's domain 2, and the inside domain is 1. Sorry, it's other way around. So you can see the solution U predictor on the right hand side, and the relative L2 error is is of the order of -3 after around 15,000 iterations. We have also solved the shock wave problem. This is oblique shock wave reflection. You can see the oblique shock which is coming from the left top corner. It hits the bottom wall and then it reflects back. So I use this peanut shaped domain. So if it basically, the shock penetrates through peanut shaped domain and then it is reflecting it back. And these are the predicted solution for pressure, density, and velocity in X and Y direction. And these are the comparison with the exact solution. So the shock is captured accurately. We have also done parallel implementation for both cPINN and XPINN. So this is again the same lead-driven cavity problem. You can see that computation versus communication time for cPINN and XPINN basically. So okay, so on left-hand side, you can see the cPINN and right-hand side is the XPINN result. So you can see both communication time is more for XPINN compared to cPINN because it's to enforcing the residual continuity condition. You have to find out the residue of the whole PDE, unlike just a flux continuity condition, which is sometime couple of order less. I mean, involves derivative that are couple of order less than the whole PD derivatives here. So that's why the communication time is more in XPINN. We have also done the weak scaling here. You can say that this is the sample per second for cPINN, for XPINN, and this is for cPINN, and they are matching really well with the theoretical values. We use till 24 GPUs basically, starting from 4. And this is the strong scaling. So you can see the speed up in cPINN and XPINN. So in XPINN, speed up is slightly less because of obvious reason, the way you are connecting the interfaces. So that's the reason. And again, in terms of efficiency, cPINN hits almost 80% and XPINN hits around 70%. Okay. So any questions? I'm not sure how much time do I have.
So we have a question from the audience, from
Yes.
Tariq. It says, is there any trends or methods when generating domains? Many is better, depends on the problem.
I'll come to that because that's a really good question. We have also done some work where we are automatically finding the subdomains, how to decompose these subdomains. But unfortunately, I'm not showing that work here. But I'll give you a reference at the end. But yeah, I mean, it's a good question. A priori, we do not know how is the solution and how to decompose the domain, but that can also be done automatically. I'll show you the reference. So this is a recent.
Wait, sorry. Then we have another question from Pankaj.
My question is a bit general about PINNs. So the examples that you have shown, it's mostly the parameter of the PD is kind of constant, right? So
Yes.
do you have any experience if it's like a spatially variable parameter, like if your PD parameter? Yeah.
Yes, I mean, we have also solved where the field variable itself is unknown. I mean, not all, but some of them. So, and at the same time, you have also unknowns in the model. So basically, you are finding the idea here is to find out the field variable, which is not constant, right? It changes with domain. So that can also be done using PINNs.
But well, my question was that, like, for example, if the parameter of the PD is variable, so like then it's like spatially distributed. So there's like, does it affect the training process because now there are like more possible combinations?
No. So basically, in that case, you have to assign that your parameter is dependent on spatially or temporally. Okay, so you cannot assume that it's a constant parameter. So it's like a field variable then, right?
Yes.
Yes. So yeah, so it's similar to finding out a solving a problem where some field variables are unknown, and at the same time you also know something about the model. So this problem can also be it can be solved.
essentially solving the forward and inverse problem at the same
Yeah,
time.
it's a semi-inverse problem. Yes.
Okay, is that okay? And yeah, and about another general question about this generalization. So, like, if once you train a PIN, then if the boundary condition or model changes, what is the state of generalization of PINs at the moment?
Well, this basically, if you see, the concept of generalization is very common in classification problems, right? So once you train the model on one data set, you can actually test it on another data set, or even if your data set, the testing data set is not coming from the same distribution as your input or training data set, then there are many methods like domain generalization, domain adaptation. But in PINs, we are solving PDEs, and you know that if you are changing the data or the boundary condition in this case, or for the forward problem, obviously, then and keeping the model same, or if you are changing the model, then you have to retrain it. Okay, but here people have used ideas like transfer learning, those, or multiple few shot learning, or continuous learning, these kind of ideas. So you can yes, but you need to retrain that. You cannot get the solution. Maybe you start because of the transfer learning strategy, you can use the pre-trained network on a similar set of kind of model, I would say. So there should be some synergy between the model you train and then the model you are going to test it, right? Then, but you have to retrain it definitely. And if you use these kind of strategies, then maybe the training cost may not be much, because the network knows something about that kind of PD already. But yes, the moment you change data, or the moment you change the model, or maybe just a few parameters in the model, then you have to retrain it. Okay.
Okay. Yeah. Thanks. Yeah. So basically, if we want to solve like complete full inverse problem, if you will, then you have to, for example, like when I solve an inverse problem, I have to solve the PD like many times, and if like maybe like few thousand times. So then it's, in this case, it's probably not possible, because then every time you need to train it.
No, I mean, here, what's your idea? I mean, when you said you have to solve multiple times,
here I'm a kind of I'm a geophysicist, so I usually I'm interested in geophysical inverse problems. So, for example, if you are solving a wave equation, but your velocity is spatially distributed. Now I want to estimate the velocity from the observed data. So I don't know anything about the velocity, but I have the data, and I have the wave equation.
Okay, one thing, it all depends on the data. First of all, if you have the clean data, then I would say solving or spin just once, I guess you get pretty much solution. But it all depends on the quality of the data and how much data you have. If you have a noisy data, then I would say then you have to go through the Bayesian PIN approach, right? Because you don't have trust in the in the data set. Then you need a multiple, there also you don't need a multiple solution. But of course, if you have clean data, and when you say you have to run it multiple times for the inverse problem, say for example, but that is required only for the uncertainty quantification. Okay, not for if you just you are sure that your data is clean and it is enough, I think you can solve just one time. I have shown some of the inverse problem where I need to just solve it one time. I didn't solve this multiple times. But yes, if I want to do UQ, I just want to have certain trust in my solution, then you are correct, you have to do multiple times. For a clean data, you can use ensemble techniques, and for noisy data, you can use Bayesian inference here, Bayesian PINNs. Yeah, so that's the idea. But for yes, if you have data, enough data and clean data, and if you don't want UQ, then I think you just need to do it one time, even though it's an inverse problem.
Okay, thanks. Yeah, sorry for taking such
no problem.
No, it's okay. Sorry, Ameya, we have another question from the audience.
Yes.
So the question is, states arising from dynamical systems are massively correlated. How do PINNs, neural network that assume IEE identically independent distributed data, taking this issue, is that through loss functions?
Your voice was
apologies for that. So the question is in the chat. So the question, I'll say it again. States arising from dynamical systems are massively correlated. How do PINNs, understood as like neural networks that assume IID data, take on this issue? Is that through loss functions?
Okay, this is an interesting question because similar to dynamical system, there are equations like Helmholtz equation. If you have a right-hand side equal to 0, then there are multiple solutions that can admit the same equation. So I would say the vanilla PIN is not with vanilla PIN. It is not possible to capture the intended solution. But it will always go towards the trivial solution. But then there are methods like homotopy pins or homo pins. They develop this. They use this homotopy method to learn these multiple solution of the PDEs by tweaking the homotopy parameters. But yes, there are methods available where this kind of dynamical system with highly correlated solutions or multiple solutions of PDE can be captured using pins. Yes.
Okay. I think we have another question from Tariq.
Yeah.
Okay.
Yeah. Sorry. Hi.
Okay.
Actually, just like one maybe general question about the inverse problems. So how can we be sure that the quantities that we predict are the correct quantities? Maybe there might be some. I mean, they can also satisfy all the equations, but maybe they are not really the solutions that we are looking for. I mean, can we be sure that really it's they are unique? For example, identified parameters.
So of course. So again, I will say the same here point. If we want to make sure the quantity that we are predicting, they are correct, or is there any other set? I mean, if there is multiple solutions for the same set of quantities, then definitely the idea is to go Bayesian or ensemble network, where you can actually gather expert advice from more than one expert. Okay. Otherwise, there is no way, or else you need to have some prior knowledge about the parameters range. So where you can expect it actually should have that kind of value. Okay. So that's the only approach you can actually use here, just to make sure that the values which you are getting is more or less correct. Any other question?
So I have one question, but I'll wait till the end to make sure that you've completed your presentation.
Okay. Okay.
Yeah, we have 5 minutes left. Yeah.
Oh yeah, I'll quickly go through this. This is a recent work we did, a unified scalable framework for casual sweeping strategies for pins, specifically for time domain decomposition. So you can see that the first figure is pin solution on A on top, and the bottom is the exact solution. So here the boundary condition is periodic. So even though pin satisfies the periodic boundary condition, it fails to propagate the solution. So in this green region where the solution is 0, it still satisfies the periodic boundary condition, right? So here that's the issue with one of the limitation of pin. Second thing, no propagation at all given by this B curve. The solution, exact solution, is on the right hand side, predicted is on left hand side. And third one is incorrect information propagation. The predicted one is again the left hand side, exact is in right hand side. So these are some of the limitations of PIN. Okay. And these are simple problems. If you see, first two problems are linear convection equation. Okay. And the second problem is Allen-Kahn equation. So there are various strategies that has been proposed in the literature, like time adaptive sampling. You can actually start with a simple domain, and then you add small domain till you actually cover the whole XT domain, and you train it accordingly. Okay. There are different strategies like adaptive time sampling, backward compatibility, time marching, and even XPIN. We have also seen that. So what's the difference between XPIN and these strategies? So here you are serially training the subdomains, and here in XPINN we are parallelly training the subdomains. Okay, and we have also know these casual weights. So basically, we are putting a defining a collocation point weight mass that moves in time, inverse exponentially proportional to the magnitude of the cumulative PD residue. So basically, we have the soft causality that can be violated. You can see I have just put these examples or these methods in this table, which actually differentiate what is soft causality, hard causality, non-causal, and this is time slab and the sampling scale. Okay, so we have different soft causality and hard causality methods. But we do not have these together. So what we are doing, we don't have anything in this column, soft plus hard. So what we are doing, we first, our first idea was stack decomposition. So we have the stack decomposition, which is in between time marching and the XPIN. So you start with a set of domains for the training, and then move on to the future training. So you can choose number of subdomains here. You don't have to choose just one or all. And the second idea was window sweeping. So here basically, this is basically adaptive time sampling and the casual weights. You can see that once in these times, so we are actually enforcing the boundary conditions in a hard sense because the weight points are large, and these are the future points which are yet to come. So here weight points are small, and this is the transition window where you are actually sweeping this weight points. You can see different kernels you can use here, like a uniform, linear, error function. Here we used error function here. So this reduces computational cost tremendously. So these two now fit in this soft plus hard causality problem. Okay, and also we use transfer learning idea. So you start once you train the one subdomain, and once you start with another, you actually use that previous trained subdomain, and you can also do the fine tuning. Okay, so I'll just quickly go through the examples. So this is a KDV problem from you can see this is the short term and the long term problem, long time integration problem. For short time integration 0 to 1, we just compare PIN, SD PIN stack decomposition, and the window sweeping WS, and together both. So you can see that they are more or less same relative L2 error. Okay, but for long time integration, you can see that the SD and WS PIN, they are much more accurate than the vanilla PIN, and in terms of training time, it is also good. So so this approach was actually good for long time integration strategy. So I'll just quickly go through this example. So in this paper, I just we have done we have actually described the generalization issues in PINs and XPIN. How the domain decomposition actually not only makes your complex solution simple, but at the same time it also divides the data. So that's an overfitting issue. In the second paper, this is the first comprehensive theoretical analysis of PIN and XPIN for nonlinear PDE, specifically Navier-Stokes equation. We have proved that just two-layer tan-H activation function, your error, the actual error is always less than equal to square root of the training error. Okay. This is the idea someone asked me. So this is for the automatic domain decomposition process. So here we use the partition of unity idea, gating networks for finding out the best domain decomposition. And I think I have shown this already. Yeah. So I'll just go through conclusions. So we presented PINs. Basically, we saw some of the applications of PINs. We also discussed adaptive activation functions and their advantages over fixed activation. We discussed domain decomposition strategies like cPINN and XPINN, which has many advantages. You can see here. And we also finally discussed the unified scalable framework for time domain decomposition based PINs. So I would be happy to answer any questions if there are. Thank you.
Oh, thank you, Ameya. It was an interesting talk. Zach, do you have any final comments?
I'm sorry, I've had to vacate the meeting room, so apologies. I just first of all, thank you so much for sharing all this work with us, and for going through so many examples. That was really nice. I just have a general question, rather, or a comment rather, about the generalization. Would you agree that the generalization of PINNs still very much depends on the representation of the physics in the data? So it is not going to discover missing physics, right? And
Yes.
And rather the loss function itself, the physics in the loss function is guiding the trajectories along the loss landscape. So I find this as of a missed opportunity to use the structure that PDEs or ODEs have, and I feel that if there was potentially more linkage with the structure that the PDEs natively have, then there could be improvements on the generalization of PINNs.
Yes, yes. But I would say the generalization is mainly because of two. One is estimation error. That's because coming from the finite set of data where we do not know the distribution of the data. And second is the approximation error. So basically that's heavily depends on the, as you said, the architecture of the neural network. So both architecture and the data, plays a crucial role for the generalization of PINNs. And here, in case if you are changing the boundary condition or the data and the PDE, then definitely you may not generalize well. But as I said, we need a pre-training here before finding the or predicting the solution on a new set of data and different set of PDE.
Thank you. Also, like I find the way we validate, so we test generalization based on model fit, predictive fit, but I think that this is not necessarily even enough to really validate the generalization of a model, because especially when we're doing models for physics applications and engineering, this doesn't tell us anything about how well have we learned the governing underlying alignment with the actual physics. So I feel like this is something that needs to be developed, and the RMSC is enough.
I think it's like a no free lunch theorem in PINNs, right? So you cannot have a single model that can solve all type of PDE that has synergies or the different type of data sets. So it's similarly in it's no free lunch theorem.
Thank you so much. I won't keep your time, keep you occupied, and also the rest who are still on the call. Unless there's any other burning questions, I would like to say thank you so much, Ameya, for sharing your work with us, and thanks to everyone for joining and for sharing, asking your questions. Are these questions? Sorry, there's a question, I believe, a quick question from Tariq or from Anish.
If may I, we don't have so much time, I guess, but maybe something quick. Okay.
Yes.
If Ameya is okay with it.
Yeah.
Okay. Sorry, I'm gonna take so much time. So my question is, for example, all the exam or most of the times I see some examples, but the parameters in those examples, they're really some small scale parameters. Because when you just really change parameters to a large number, I guess it just stacks, the optimizer stacks it at some point, and you have to make some tricks. And this is also the case for domain decomposition PINNs. I'm not talking about the domain, I'm just talking about the parameters, for example, like maybe some ring numbers.
Yes. So there is one more paper, not from our group, but they have actually done the domain decomposition in parametric space. Okay. So that's the idea, to tackle a very high dimensional parameter set or parameter space. So that also can be done. That also can be tackled using domain decomposition of the parametric space, not the physical space.
And can you please just tell me the maybe send me the name of the paper, or if it's
I have to, I can send it to Zach or Andreas. I need to find it out. Yes.
We have another question from Manish, and then from Carlos.
Hi. Yeah, my question is, well, firstly, thank you very much for the presentation. It's really interesting. My question is around, how is there any other use cases you can mention from your research, like you've given the example of the waves?
You mean to say the examples from, I mean, related to wave equation or what?
Yeah, like this kind of bridge between PDEs and neural networks. What other examples have you found, like real world applications
Okay,
research?
okay. So we have also solved examples from turbulent flow. Now the idea is to use the DNS data to find out the constitutive relation or the parameters in the constitutive relation. So you can see that the DNS data is huge basically, and fitting that kind of data in a single GPU, it's not an easy task. So what we have is the time, both spatial and temporal data. It's in terabyte, and there we have used both cPINN and XPINN methods to to infer these parameters in the constitutive relation. So these kind of we also working on the gravity flow problems. So again, their aim is to again, it's an inverse problem. The aim is to infer the concentration, which is actually a field variable. It is not a constant. So what I have shown here, it's simple problems, but yes, people, and of course, many people outside of our lab, they have solved many different problems, inverse problem using PIN. So there are so many applications where PIN was employed.
Great, thank you.
Thank you very much. So Carlos will take your last question.
Hi there. I think, can you hear me?
Yes.
Yes.
Okay. So I'll be very brief. First, I wanted to ask you if you could just go back a few slides just to quickly save some of the references at the end that you had, because some of them are new for me. So okay, so that's good. And if you can go to the XPINN theory and the next one, I think there was one more.
Oh yeah, this one.
Yeah, perfect. And my second question was, I suppose, very related to the previous one you just got. So do you think, is there any viable applications for PINNs in solving the forward problem for PDs? Can they compete with classical methods in any case?
That's a good
For
question.
the forward problem. For the inverse problem, obviously, I can see the use of it, because like classical methods, you cannot really easily integrate data or anything like that. But for the forward problem,
yes. So, well, if you for forward problem, definitely with vanilla pins or recent advances in pins, it's the training time is large. But I would say there is one more recently. They proposed this, I think, S-spin or splitting spin strategy. So what they actually use the eigen summation basically. So they use tensor product, and they have shown that they are faster, around 100 times faster than vanilla pin. It's a huge number basically. So people are working on, this is still an underdeveloped technology. People are working on pins and coming up with new methods. But as of now, there are very few work for specifically for forward problems, where they can, of course, they cannot compete for all kind of problems. But yes, people are working on in that direction. So one example is separable pin, not splitting spin, separable pins, S-pin. Okay. So this is the recently published paper in arXiv, maybe 6 months back, 6 or 8 months back. But they have shown that they have actually accelerated around 100 times faster than vanilla pin.
nice. Wow, that's impressive. That's nice to hear.
Yes.
Thanks a lot.
You're welcome.
Thank you, Carlos, for the question. So we'll call it a day. Thank you so much, Ameya. If it's all right with you, we will upload this on our channel. We will contact you more formally about it. But hopefully, if you're okay with it, it will be uploaded to the Turing page. In the meantime, thank you to everyone for joining, and we'll see you next time.